and some of the mitigation techniques. And these power quality issues are the problems that are concerned with the current quality in general. And we would look at some of the existing compensation algorithms, by which I mean that we would look at the range of algorithms that have been proposed from 1970s till 2002 or 2003, and see which techniques have been effective in what context and what are the drawbacks of certain algorithms and certain theories that have been proposed. And next we look at the realization of the shunt active power filter. The shunt active power filter is also called as the DStatCom, or the distribution static compensator, and this is nothing but a voltage source inverter operated in a current control mode. So we look at how the active power filter is being realized. And since this is an inverter, obviously the current control technique that is adopted for the inverter is very crucial, and we'd look at some of the current control techniques and how some improvements can be brought about in multi-level power converters. And we'd look at some of the issues that arise out of certain topologies of the inverter, and we'd look at some of the solutions. And finally, the validation is done by means of simulation and experimental studies. And even though this has been given towards the end, we'd look at after every concept, looking at the corresponding simulation and the experimental results. And we would spend more time on these two aspects, the inverter current control techniques and the issues. So let's get introduced with what is power quality. The IEEE standard definition, which is 519, defines power quality as the concept of powering and grounding sensitive electronic equipment. This was in 1992, and then we have had revisions of this standard 519-1992. But we know that the power quality has evolved over time, and this is very restrictive in definition, because this restricts power quality to just the grounding issues. But power quality has evolved over time. And so we look at a much broader definition of power quality, which is much more comprehensive. This is from a recent text by Professor Srikanthan, published by the CRC Press. And he defines power quality as a set of electrical boundaries that allows a piece of equipment to function in its intended manner without significant loss of performance or life expectancy. So in short, any power-related problem that compromises either attribute, which is performance or life expectancy, is a power quality concern. So this is much broader. Even though the term power quality is much broader, for the today's talk we would look at the problems associated with reactive power, harmonic elimination, and load balancing techniques. And this is not an advertisement for Fluke, just to show that this is a power quality analyzer, and this was what I used during my master's research. And now going on to the specific power quality issues, we look at unbalanced, reactive loads, and nonlinear loads. Nonlinear loads are the ones which are, let's say, a power electronic load, let's say for example a three-phase rectifier, which would draw currents which are non-sinusoidal in nature. Or in other words, the currents that are drawn from the supply have frequency components other than the fundamental frequency components of 50 Hertz. So since this thesis was done in India, for all the simulation and experiments, I would use 50 Hertz, which is the fundamental frequency of the supply in India. And looking at the effects of these unbalanced, non-reactive and non-linear loads, we know that they give rise to poor power factor because of the presence of inductive or capacitive elements. And harmonics, this is because of the power electronic equipments, because they tend to draw currents which are non-sinusoidal in nature. And the imbalance is because of the unbalanced loading of the three-phase systems. Even in the Everitt Lab, we can see that there is a huge quantity of neutral current that flows through the fourth conductor, which is a three-phase four-wire system. And sag and swell is not something we've discussed today, because these are voltage related. These are more the current related problems. The sag is a dip in the voltage, and a swell is an increase in the voltage for a certain duration of time. IEEE 519 defines it as 0.1 to 0.9 per unit for about 0.5 cycle to 1 minute. That's the duration for which sag and swell is defined. And flicker is a phenomenon that happens, for example, let's say turning on of an induction motor direct online. This would tend to draw a huge inrush current. So this would cause a huge voltage drop across the feeder impedances, and hence the other loads which are present on the distribution end would suffer a voltage dip and gives rise to what is called as a flicker phenomenon. So what are the adverse effects of poor power quality? Obvious. One is excessive neutral current, which means that, let's say there was a balanced system of currents, IA plus IB plus IC is 0 for a three-phase balanced system, because there is no current in the fourth wire. And this is good because the neutral conductor is not stressed to any limit. But when we have excessive neutral currents, the neutral conductor has to be rated accordingly, and the resistance of the neutral grounding is also of concern because that gives rise to losses. And so obviously we want to eliminate this. And increased power losses and overheating. Let's say our loads are taking up harmonic currents from the source, and these source currents are in turn, they pass to the distribution transformers and so on. And we know that the hysteresis and the eddy current losses are direct functions of frequency. In fact, the eddy current loss is is directly proportional to the square of the frequency term, and the hysteresis losses is about 1.6, which was empirically defined by Steinmetz when he was in General Electric. And the third effect is erroneous meter reading. We know that the presence of smart meters which tend to make use of digital algorithms to compute the active power, if the frequency is wrong because of, let's say, corruption or distortion in the voltages, this would give a wrong reading because these digital algorithms tend to make use of what is called as averaging filter, sampling and averaging. So, but if this average is computed wrongly, then it obviously means that the active power that is recorded by the meter is wrong. And malfunctioning of devices is of more general nature. This could happen for any sensitive loads. For example, there are hospital loads which will definitely demand a beautiful set of sinusoidal voltage waveforms, but if you are not able to do that, it can potentially result in malfunctioning of these devices. And communication interference happens predominantly where the telephone lines or other communication lines, they flow parallel to the conductors. In India, in fact, we have the telephone lines flowing in parallel on the same pole, so which means that these harmonics can have interference on the telephone lines, and this has to be obviously avoided. So this is just the output of the three-phase fluke meter which was shown before, just to show how the waveforms look like in a power quality analyzer. And these are some of the problems now. Let's look at what are the mitigation techniques. These are called as compensators. So from the literature, we just grouped as to what these techniques are. One is passive filters. We know them for sure because they have been time tested and they are very rugged and so on. So the obvious advantages are easy design because once we know the frequency, all you have to do is find the cutoff frequency and design the LC component so that you get rid of the harmonic components. Reliable because they don't have any switching components. They are devices. They are just passive devices which don't cause any trouble. And they are cheap because they are being used for a long time. And the obvious disadvantages, they tend to become bulky, and because of that, they have equivalent series resistances. What we call as capacitor banks and inductor banks are not ideal devices. So they tend to have equivalent series resistances. So a loss also happens in these equivalent series resistances, and cooling has to be done for certain high power reactive compensators. And they are fixed compensation, by which I mean that let's say you've decided the values of L and C for a filter, there is nothing more you can do about that except when you make some switching. So they are fixed compensation in general. And resonance problems and capacitor aging happens because of the fact that the capacitance tends to vary over time. So whatever the frequency that was tuned would not be the frequency that is desired, and so there is unwanted resonances in different parts of the frequency spectrum. And this is an evolving technique, and we've already had a lot of manufacturers doing active power filters or static compensators. There are three main power filters. One is called as a D-StatCom, which is a distribution static compensator, which takes care of the problems in the shunt, by which I mean current related problems, power factor improvement, load balancing, and harmonic elimination. DVR is more a voltage-based technique, which is used to compensate voltage sag and swells. What this does is we insert a series voltage along with the supply voltage. Let's say whenever the supply voltage suffers a dip, this inverter pumps in a series voltage along with the source. They tend to add up together to create what is the nominal desired load voltage. So that's the action of DVR. The UPQC is an analog of the UPFC, which is used in FACTS, which is the Unified Power Flow Conditioner, and here it is Unified Power Quality Conditioner, which is a combination of these two. So it means that the use of D-StatCom and DVR together is going to solve all the voltage and the current related issues. The obvious advantages are they are multifunctional. They can eliminate harmonic currents, they can improve the power factor, and they can make the load balanced, which means that the three-phase supply system sees the load as a balanced set of quantities and thereby eliminating the neutral current. So that's what it does. So it's compact in size. For example, if we compare the size of a certain megawatt mega MVAR reactive size with respect to the same capacity of an active power filter, this tends to be smaller than this. And dynamic compensation is possible. Here it is not, because let's say when the load changes suddenly, the inverter can compensate adequately for the dynamics, provided the current control technique is designed to be robust enough. The disadvantages are complex in design. This happens because of the control algorithm and not because of the controller. Because controller is not a problem, because we've had high performing, let's say, signal processors on which these algorithms can be easily dumped into. But the problem is in developing compensation algorithms, what should be the set of currents that need to be injected into the system so that you get rid of all these problems. Expensive because of the reason, but now it is really not, because we have switching devices which can handle considerable voltage and current ratings, but they are still cheap. I mean, we can see evolution of IGBTs over time, which are proving to be quite cheap. For example, there is an IGBT from Mitsubishi, which is CT60AM18F, which costs about $4, but has a capacity of about 700 volts in withstand voltage and 60 amperes. So they are not actually expensive. The hybrid is just a combination of these two. So the idea is, let's say you have a band of harmonics to be eliminated. Some of them are taken care of the active power filters. And let's say the smaller components, the components which don't create too much of trouble, can be compensated by the passive filter. They are just a combination of these two. The shunt hybrid active power filter is just combination of D-STATCOM with the tune filter, and the series is DVR with the tune filter. And the shunt series is which one you place first. It could be the series DVR first and then the shunt D-STATCOM, or it could be the shunt D-STATCOM and the series DVR. Both of them have different functionalities and different control techniques have to be employed. They are not the same. This is a schematic of a D-STATCOM. Henceforth, we would look at specifically the aspects of D-STATCOM. So we have, for this case, we assume balanced sinusoidal set of voltages, which is quite reasonable, because when you look at the main supply voltages, they are close to 60 hertz and they are sinusoidal and they don't have harmonics. To be honest, they have very small harmonic components, but for all practical purposes, we can assume they are balanced sinusoidal. This is the unbalanced reactive or nonlinear load. So virtually any load, any kind of load this could be. And shown here is the ideal compensator, which is the D-STATCOM. Here it is shown as a set of 3 current sources. So which means that, let's say by some means I'm able to compute this IFA star, IFB star and IFC star, which is the filter currents. So F denotes the filter currents in A, B, C phases. Let's say I inject these 3 currents into the PCC, which is the point of common coupling. I get rid of everything, get rid of all the harmonics, imbalances and the reactive components of current. And the source currents, ISA, ISB and ISC, they become balanced, sinusoidal and in phase relationship with the source voltages, which means that we achieve unity power factor. So this is the schematic of this. We'll look at later how this is implemented. So this is a 4-wire system, because we take the neutral wire out and then we connect it to the compensator, and this also goes to the source. Yes. So in the previous slide I was talking about what these, I said let's assume we have computed a set of reference currents that need to be injected into the point of common coupling. And these are some of the techniques that have been proposed so far, which help us in computing what these currents are. The first, we would look at only the first and the second and the final one, because they proved to be some of the turning points which generated a lot of literature. So the first one is average and sampling techniques by Guy, and the instantaneous reactive power theory. This was almost quite beaten to death, and there are some interesting facts and phenomena about this theory which we would look in the later slides. And this instantaneous symmetrical component theory by Professor Ghosh in 2000 proved to be very helpful, in the sense there wasn't any transformation that was involved in computation of the currents. When we look at some of these reactive power theories, most of these theories are either in the transform domain or the frequency domain. So what most of the papers do is do a fast Fourier method and compute what is the amplitude of these harmonics are and the phase relationship. So obviously, when a 180-degree phase relationship current is injected into the PCC, both the harmonic components get cancelled out so that the source is balanced and sinusoidal. So that's the idea behind the frequency techniques. But we know the problems with the frequency techniques because you need to have a correct value of fundamental. The fundamental frequency extraction becomes a problem because the frequency is not really 60 Hertz. It can go from 59.8 to 60.2. So that needs to be accounted. So in terms of robustness, these three techniques are really good. There was one in 2006, but it was a modified version of this. So it was an extrapolation of this because this theory assumes balanced and sinusoidal voltages. So the author has said even in the presence of distorted and unbalanced voltages, we can use this theory. And he says we'll make use of positive sequence extraction, and the theory works. So it is just an extension of this theory. Apart from this, there were a couple of papers in 2011 which talked about extended instantaneous reactive power theory. So there was another component that was added, but it is just extension of this theory. So if we understand these, it's almost we could formulate many theories because this problem can have sub-problems. We can assume the voltages are unbalanced and distorted, and we can assume that they are subject to sags and swells, and it could be extended to any number of problems. And these techniques could be again extended for those extended problems. And this is the sampling and averaging techniques. The idea is very simple. In the paper, it talks about delta load, but this holds very good and equally good for even star-connected loads. So this is these are the loads by the user, and these are the compensators that are connected in parallel. So the compensators will look like this. They have variable susceptance. So it could be made capacitive or inductive depending on how you switch these thyristor devices. These thyristors are not high frequency switched, rather they are just line frequency switch, 60 Hertz switching. So they are applicable only for steady state conditions. They cannot be used for transients because of the limitation of this thyristor by itself. And this can eliminate only the fundamental reactive power. And it cannot do for harmonic reactive power because this does not understand what it is. And this is the corresponding paper for that. And since these are the drawbacks, but it was used for quite some time till 1983-84 when the next theory started coming into picture, which is the instantaneous reactive power theory. And for people who work in machines and drives, we know that alpha beta zero transformation is very commonly used. It studies a three-phase time varying sinusoidal components as a two-phase system, which can still be, if it's we call this as a stationary reference frame transformation when we analyze machines. So every component becomes simpler in analysis when you do this transformation. And okay, let's look at this picture a little later. So I haven't given the value of the active power and the equation for active power and reactive power, but active power is defined as V alpha I alpha plus V beta I beta. And reactive power is defined as V alpha I beta minus V beta I alpha. And this is the understanding in the transformed domain. Alpha beta zero phase, and the source, this is any load, and this is the compensator. So the source supplies only the balanced active power. It doesn't even supply the reactive power, it doesn't supply any harmonic power. But this compensator supplies the Q, which goes back and forth, because that's the meaning of reactive power. And the delta P is just the P loss, because this compensator is not ideal. There are certain resistances in the switches and resistances in the inductor also, which is used inside. So that will have a little bit of losses which are compensated from the source. And this is the oscillating component of the load power and the oscillating component of the zero sequence power. But these definitions are hazy, and there isn't a reactive power definition for three-phase systems yet for unbalanced systems and distorted systems. There have been many theories after this. For example, there was Boudinot's version of reactive power. There was Fry's version of reactive power for distorted and unbalanced systems, but they still don't hold good for many conditions. Even in this case, the author does not talk about distorted supply voltage, and this theory fails miserably for distorted supply voltages, because when we transform the reactive power into three-phase system, the equations tend to assume the form V IA times IB minus IC plus VB times IC minus IA is cyclic, which gives 3VI sin phi, which was the point of contention in Boudinot's version of reactive power. Because Boudinot says 3VI sin phi is just the peak value of the oscillating component of the reactive power, but 3VI cos phi is the average component. Even though for convenience, we tend to make use of the fact that 3VI sin phi the whole square plus 3VI cos phi the whole square is VI, which gives the VI rating. But it is not so. This is the paper. And I would strongly recommend, if people are interested in reactive power theory, these are two papers that were published by Professor Zarnicki in Louisiana State University. And he denounces, in fact, one of the titles, what is wrong with the Boudinot concept of reactive and distortion power and why it should be abandoned. The abstract is so, I have never seen papers which talk so vehemently and opposes something like this, because Boudinot's power was there for about 70 years, and this is a beautiful exposition of why it is wrong. And when this theory is applied for a perfectly resistive network but unbalanced resistive network, this instantaneous reactive power theory gives reactive power, which is absurd, because we cannot get reactive power in resistive networks, because the unbalance in the system is being thought of or is being understood as reactive power by this theory. So he denounces this theory also on some misinterpretation of the instantaneous reactive power theory. In fact, he doesn't propose a solution, but he is discounted what is all not correct. So these are very interesting papers. It is not abandoned, but the author proposes a strong reason why it should be abandoned. Because but people have not used Boudinot concept profusely after that, because before this 87 period we see a lot of definitions using Boudinot's version of power. But after that, there aren't many papers that talk about the Boudinot version of reactive power, which is S equals root of P square plus Q square plus D square, where D is the distortion power. For practical purposes, we can say abandoned, because there isn't much literature that talk about it after this period. Because it was a very strong opposition to this theory. And this is the instantaneous symmetrical component theory. This works perfectly well. The main features of this theory is it's very simple in formulation. It's time domain. You don't have to worry about a transformed alpha beta 0 domain, or you don't have to worry about transforming it to frequency content. And there is no transformation, and there is no definition of reactive power. There is no such thing as reactive power or distortion power defined in this theory, because we look at the theory and you will see the beauty of how it is formulated. The objective is to have balanced and sinusoidal source currents, and we need controllable source power factor, which was not possible in many theories before. Now this controllable source power factor is because of the reason that, let's say, you have synchronous condensers, which are synchronous machines operated in overexcitation mode. You can actually you need not have unity power factor, because some of the reactive power is already compensated by your synchronous machine. So we have a controllable source power factor, which is quite good. And the source supplies only the average part of the load power. And we know the beauty of the three-phase system is that for a balanced set of voltage quantities and current quantities, the P of T equation, power as a function of time, is VA-IA plus VB-IB plus VC-IC in time. This will be a constant whatsoever for every instant of time. This is going to be a constant value, even if there is reactive elements. You can try writing the equation and find it for yourself. That's one good thing about the three-phase system. So the source now is made to supply only the average component. So that itself makes the voltages so going in the reverse direction. If we ensure these three conditions, the source supplies only the sinusoidal balanced components of currents with unity power factor relationship. And it's very simple in implementation. This is the corresponding paper. And a small, not very detailed mathematical formulation, since we don't have much time left, because we have so many interesting results of the simulation and experiments. So these are the conditions that we impose. These are what we can call reference source currents. Right now the source currents are supplying reactive power and harmonic power and so on. But now this is the condition that we want. They have to be balanced in sinusoidal, because zero sequence current is absent. One important point to be noted is zero sequence current has a physical meaning in power systems because it's a neutral current component, but zero sequence voltage does not. When I say VA plus VB plus VC, it has a definite equals Vn, let's call it some other voltage. It's not the neutral voltage. It's a neutral current here, but it's not the neutral voltage, and it holds good only for one case. You can use the Millman's theorem to prove that. But for controlling the source power factor, this is the fundamental positive sequence. We can define the positive sequence voltage as 1 times VA plus A times VB plus A square times VC, where A is defined as this. And then we impose this power factor relationship, where C is the cosine inverse of the power factor, or in other words, this is the power factor angle. And source is made to supply only the average component. So once these three conditions are ensured, we combine them in this matrix form, and this is the final result. So just these three equations have to be implemented as far as the compensator algorithm is concerned. IF A star, which is the reference filter current, B star and C star, which is just these equations. And for this case, we've just assumed unity power factor is what is desired. So phi becomes 0, so gamma becomes 0, so this term wipes away. And we have delta and PL average. Let's look at delta. This is VSJ square. So it is just instantaneous squaring of the supply voltages and adding them together. VSA square plus VSB square plus VSC square. In three-phase system, again the beauty is that this component is always 1.5 Vm square. You can do the math and find it. And it's always 1.5 times Vm square, where Vm is the max value of the voltage. So if we assume the voltage is not going to change, we can as well not do this computation on the DSP because you don't have to sense the voltages. You can just plug in 1.5 Vm square directly. And this is how average power is found. We know that for one cycle, this is the equation of P of T, and we average it over one fundamental cycle. This gives average active power. And we start with the simulation studies. And when I showed ideal current references before, they were just current sources. But now this is a voltage source inverter operated in a current control mode. So this is a two-level inverter, and these are called as interface inductance. The inductance becomes necessary because we have to do tracking. And tracking for a current is possible only if there is dynamics in current. The dynamics for a current is ensured only by an inductor. So that's why this inductor is necessary. And this is called as split capacitor topologies. Right now, we assume these voltages are equal, but we'll relax this condition later. And this is a typical load. The loads can be unbalanced, and they can have a three-phase rectifier load like this. And this is how the implementation goes. Let's say we've extracted a certain reference current that needs to be injected from the inverter. We tend to use hysteresis current control because all these applications need fast response. And hysteresis control by itself is the bang-bang solution of a minimum time control problem. So that's why we use this. Let's look at how this works. This is the reference current for a small interval, and I need to track this current. So in each phase, when I turn on the top switch, a positive voltage applies across the inductor. So the current starts increasing because V is L di over dt. V is positive, so current starts increasing. And we create two bands on either side of the reference current, which is very small. So when it reaches the topmost boundary of the hysteresis band, we turn on the bottom switch. So negative voltage is applied, and then it starts decreasing. And this is repeated for infinite time. So the average of this current in this interval is this. So when the band becomes smaller and smaller, this is almost equal to the reference current that needs to be tracked. But of course, it results in high switching frequency, and we'll see some of the techniques that can do away with that. So this is just the implementation in the signal processor. And we saw the hysteresis control for a two-level inverter has the drawbacks of wide switching frequency variation. It's aperiodic switching, and the switching frequency variation is quite huge. So we just look at if multi-level inverters are used, would we be able to get any advantage is the question. This is a three-level inverter. It's a neutral point clamp topology. There are 4 switches in each leg. So when the top 2 switches are on, we get a voltage of plus VDC. And when the bottom 2 switches are on, we get a voltage of minus VDC. When the middle 2 switches are on, we get a voltage of 0. So there is an extra state that's possible with this inverter. So this makes it a 3-level inverter. And now we'll have to formulate a hysteresis current control algorithm for this 3-level inverter. This is how it's done. let's say we have the same reference which is shown as a black line here, and we create a small dead zone on either side of the reference current. This is called as a basic 3-level scheme. It already is there in the literature. And as earlier, when I reach the bottommost boundary of the hysteresis band, we apply a positive voltage and the current starts increasing. And when it reaches a value within the dead zone of this interval, a zero state is applied. And this is repeated periodically, and when it reaches the topmost boundary here, we give -1, 0, and so on. This is repeated over time. But you see there is a certain drawback with this scheme, because in the earlier case, we saw the average was almost the same as that of the reference. But now the average of this blue line, which is the actual current, is either lesser than that of the reference current, or in this side, it's higher than that of the reference current. So there is a tracking, which we call as a tracking error, because this is just a state regulator problem. So there is a tracking error associated with the basic 3-level scheme. And what we propose right now is the dead zones which we saw on either side of the reference current, we push them to the ends of the outermost hysteresis bounds. So you can see that this boundary has been pushed here and this boundary has been pushed here. So when we do this, the resulting scheme of tracking will be like this. There is a small error that's still there that cannot be avoided, but one can say that, okay, let's make this dead zone push up all the way up to here. But there is a drawback which will be seen because of high switching frequency components, which we will not see right now. So all we need to know right now is this frequency reduces the average tracking error, and the switching frequency is reduced because of the use of zero states. So this is the simulation parameters that we have used for the system. So a balanced supply voltage is used, and a linear load which is unbalanced is used, a non-linear load, and interface inductances, and so on. These are the simulation results. The voltages are balanced and sinusoidal, and these are the load currents. The 3 load currents are obviously unbalanced and non-sinusoidal, and there is a neutral current which is not shown here. And these are the reference currents computed by the algorithm, which is the instantaneous symmetrical component theory. And once we do the compensation, the source currents have become balanced, sinusoidal, and with unity power factor relationship with the source voltages. So the objective is achieved. So let's do it for the transient case to see if the theory works even in the transient condition. Here we've just turned on the linear loads and just preserved the nonlinear loads here. And the compensation is also instantaneous, and the source currents still remain balanced and sinusoidal with UPF relationship. So it works for any load. This fast response was made possible because of the moving average filter. Let's not look into the moving average filter, because the maximum time delay that is incurred is only 0.5 cycle, because we have only the odd harmonic components because of the symmetry that is achieved in the loads that common loads. So it's mostly 0.5 cycle. But if there are even harmonic components, if at all they are, then we would need 1 cycle. So at the most it's 1 cycle in the worst case. So let's look at the switching frequency variation. This was for a 2-level scheme. This has a wide variation from about 20 kilohertz to about 10 kilohertz. The basic 3-level scheme gives us a huge advantage, because here we don't have any switching, which means the switches are, even though we have more switches in one leg, the switches are off in this portion, and the switching frequency is reduced. And the improved 3-level scheme gives us the same advantage as the basic 3-level scheme as far as the switching performance is concerned. We will not discuss the limiting case because of this reason, because we see high frequency components when we make delta equal to H. So we will not look at that. So this is important. So this is the crux of the entire story. For the 2-level scheme, the THD is total harmonic distortion, which indicates how much of harmonic components is there in the source currents. And RMSE is the root mean square error, which is directly proportional to the tracking error. And switching number is 1 turn on plus turn off. So higher the switching number, higher is the switching losses. And this is the maximum switching frequency, average, and standard deviation. In the 2-level, we get very good performance in terms of tracking error and THD. They are pretty low. The 519 standard mandates a maximum THD of 5%. So they are all fine as far as the performance is concerned. So, but the switching number and switching losses are quite huge. But the basic 3-level offers us advantages in switching performance, but tracking is very bad. because of the average performance behavior. But the improved 3-level scheme incorporates both the advantages of the 2-level as well as the basic 3-level. So the objectives, in fact, the good things about both the 2-level and the basic 3-level are extracted. This is the experimental result. The source voltages are balanced in sinusoidal. This is a non-sinusoidal component of load current. We see a neutral current in the 4th wire. And these are the currents injected by the filter. And once these currents are injected, the source currents become balanced sinusoidal and unity power factor with the source voltages. This is clear. So the objectives are satisfied. So these are the gate pulses. We can see that there is a gap in the gate pulses because they are not, they don't switch during these intervals. They tend to minimize the switching losses of the inverter. And we saw this earlier. This is just for a 3-level, and the earlier one was for a 2-level scheme. The expanded view of tracking shows that how the +1 state and 0 and -1 occur. This is important to study why the switching losses have come down. This would explain that. The transient is also studied, and this is just exactly the replica of the simulation results, because for the paper the reviewers wanted both of them to be done at the same level. So this is you can see that the compensated source currents ISA is sinusoidal still, and you can see the performance is good. So now what? This is a crucial, the problem that I wanted to discuss. In higher level inverters, this is a string of capacitors that we tend to use. So these voltages were so far assumed to be of equal magnitude, but they are not in practical. They tend to drift in voltages apart from each other. Now one can ask, why is that? This is because of the reason that when the neutral wire is attached to this point, there are certain loads, like there were earlier versions of the LCD projectors which were using half-wave rectifier circuits which were contributing to DC components. And there are, I don't know how many of you use hair dryers. The earlier version of hair dryers before 1995, they had half-wave rectifier circuits. They tend to draw DC components, which can be clearly seen. And so what we see here is, because of the flow of DC component current here, either this voltage would tend to decrease or increase. One of the two will happen simultaneously. So we compute what is the average value of the current in this line. So the idea is just this. The total voltage is always a constant, which is ensured because this inverter supplies only reactive power. It doesn't supply any active power. So there is no chance by which the capacitor voltage can discharge. It will remain constant because there is no active power drawn. So now let's say there was a positive DC component. If there is a positive component of current through this capacitor, the voltage will increase. ISC dV over dt, and dV is positive, which means voltage would tend to increase. This would decrease because this goes in this direction. So now we have excess charges here, we have deficient charges here. The idea is to make use of this chopper circuit so that the excess charges are transferred from this capacitor to this capacitor. That's the fundamental simple principle. So we switch this circuit in such a way that we transfer this charges here so that both are maintained at the same value of voltage. That's the basic principle behind this. So there were some of the existing techniques which talk about switching of space vectors accordingly, but this is not possible for current control. Let's not look into the details, but this was suggested by Fang Shengpeng. The paralleling of capacitor cells is, if there are capacitors of different voltages, you just try to make them in parallel, because the final voltage equation is C1 V1 plus C2 V2 plus C1 plus C2. So which will mean that if C1 and C2 are same, they would be regulated to half of the total voltage. So the purpose is achieved, but it results in huge current, because when you parallelize capacitors, the transient current is quite huge. There are some other models using the chopper, but the computation is quite involved because it uses a state model for all the computation. Now this is what is being done in this work. We know that the total voltage is being regulated by an external PI controller. Now we look at the positive error. In this case, let's say there was a positive DC component. This suffers increase in voltage because this capacitor will have increased voltage level. So we compute the error, which is VDC ref minus this voltage, which will be positive. So that error term is compared with the triangular carrier waveform. And we don't have to worry about anything else because this triangular carrier is going to regulate the duty ratio. It's a closed loop mechanism. So the duty ratio will vary accordingly so that your voltage is always tending towards the reference. So the objective is achieved. And what happens is the average current that was flowing in the DC current was taken out through this chopper circuit. That's all happens. Let's look at the simulation results. Source voltages are here, and I introduced a certain load which consumed DC component of current. So one of the capacitors tends to charge up, and the other capacitor tends to discharge, but both of them remain at the constant voltage. The load currents are obviously, you can see the neutral current is shifted. It has a DC component, and then because of this, if we don't compensate it by the chopper circuit, this is what happens. When the capacitor voltages tend to drift away from each other, the compensation becomes poorer and poorer. The earlier objectives are not accomplished. So what we do is we use the chopper circuit and we turn this on. We just look at the dynamic compensation here. When the chopper circuit is turned on, both the voltages, they tend to come back to the reference values, and the source currents become balanced sinusoidal with UPF relationship with the source voltages. This is the chopper current. So this was just taken to illustrate that the average value of this current is exactly the same as the average value of the current flowing in the neutral conductor. And these are the experimental results. We see that there is an average component for the fourth wire, and they have harmonics also. And this is, yeah. Yes. Yes. This is because in the earlier case, here was one simulation where we show what are the adverse effects if we don't compensate. But here I turn this on at this point, 0.7 seconds. But once it reaches, it takes some time because of the delay in the chopper circuit. It takes quite some time to settle down. So I have just captured the final 2 cycles of the waveform here after the voltages have reached their reference values. So both in fact, this holds good even for 0.98 to 1. So the scale is only different, but it happens after the voltages are equalized. Yes, yes, that's the driving point. Once we, because if the equalization does not happen, this is bad, as like this. Once, okay, and this is the experimental result. So here the half-wave rectifier circuit, which was like a hair dryer, was turned on here, and so the capacitor voltages start to discharge, and you can see the compensation becomes bad. The neutral current, which was expected to be 0, is now jumping up because the compensation was not good. And once I turn on the chopper circuit, this is after equalization. So we see that the steady state after, you can see VDC1 and VDC2 are regulated to the reference values, and the current, this is the chopper current, the average of which is exactly the same as the DC current in the neutral wire. And we see compensation becomes what is expected. Yes. And some of the industries, there are a lot of manufacturers for static compensator. This product, SVC Lite, was introduced in 2010 by ABB, and they have done a voltage compensation also. They make use of another inverter which has inserted in series. So active harmonic filtering, voltage control, and mitigation of furnace transients, and so on. And the largest installation was found in 65, installation 65, this is the capacity in Chile in 2011. And this is manufactured by Nokian Capacitors, which was subsequently taken over by Alstom. And they also manufacture a similar static compensator. But most of these tend to make use of algorithms which are not really good in the dynamic states. If the load variation is quite huge, they cannot take care of that. Yes, yes. So this is the source from which I've just quoted from the website, verbatim. No. but no way an advertisement for ABB or Alstom. And so I'd like to conclude. So far in this presentation, we just looked at some of the power quality issues and mitigation techniques, and we looked at some of the existing control algorithms, and the mathematical formulation for this one theory was seen, and the advantage of this theory was also clear. And an improved method of control using the 3-level inverter was also suggested, and a carrier-based, which is a triangular waveform-based error control to achieve voltage balancing in split capacitor topologies is also suggested. So these are the main points that I wanted to discuss for today. So in probably a couple of months from now, I'll talk about the research that I've been doing here. So any questions on this, I can take now. We still have 5 minutes. Okay. Thank you.